So, so I will talk about T-duality with flux. So the main topic of this, one of the topic of this meeting is mirror symmetry. Okay. So, but in most talks about mirror symmetry, both sides you still have geometric structures like Kähler or complex structures, this kind of thing. But here I'm talking about what's the topologic content of the mirror symmetry. So we forget all those geometric structure, but only left with topology and the flux. Okay. So okay. So I would mainly introduce my work joined with Mathai recently. So this is our paper. So this paper, so we wrote it motivated by mainly motivated by these three papers and some papers in the reference. So the first two are the Attia's paper and the Bouwknegt paper. So that is to understand the Attia single index theory from the perspective of loop space. Okay. So basically, they study equivalent cohomology of loop space. So because we know that consider the free loop space, at least there's a circle action on it. Actually, there's also Morasoro action on it. But if you study this infinite dimensional manifold with circle symmetry, so then you can do localization formally. So then you can visualize the Attia single index zero. Okay, so this is the early development. So another angle of the theory was the T-duality with H-flux formulated by Bouwknegt-Evslin-Mathai and Mathai. So this is a paper. In this paper, they formulated topologic T-duality with H-flux. Okay, so we will combine some index theory point of view and the T-duality. So we wrote this paper. So here, let's see, here the T-dual pair for them, so actually has a much less structure than the Euro mirror symmetry. So here we consider two circle bundles, only principal circle bundles over same space. Okay, on the left-hand side, on this circle bundle, we equip it with a connection and then a flux, three form. On the other hand, on the other side, you also have a connection and a three form. Okay, so as this three form, as pointed out in the first lecture given by Professor Yau, in the Kähler case, actually there's no flux. The flux is equal to zero. But when you do non-Kähler thing, the flux comes out. Okay, so actually this flux has a very strong physical meaning. Okay, now these two circle bundles with this data, they are called a T-dual, topological T-dual pair with flux. If these two sides, they constrain each other in this way. So you see this is the three form. You integrate along the fiber. The fiber is a circle bundle, then you get a two form on the base. We require this two form is the curvature of this connection on the dual side. So similarly, if you integrate the flux on the head side, then you get a two form. You require this two form equal to the curvature of the left-hand side. So these two sides, they constrain each other in this way. Okay, so we consider such a pair subject to such a relation. So then we call it a topologic T-dual pair with H-flux. Okay, this is a very simple model. So then you may ask me why we only consider circle bundle. So of course you can consider torus bundle or higher torus bundle. But to study topology of both sides, there's not too much difference actually. And also you may ask me, this is the two circle bundle over same space subject to this relation. Do they have same topology? The total space of Z and Z hat. So do they topologically same? The answer is usually is no. So for example, an example is X, you take X to be S2. And then on S2, there are two circle bundles. One is a trivial one. The other one is a hopeful circle bundle. So you know S1, S2 times S1, the triple bundle, and the Hopf bundle, whose total space is S3, they're very different, but they fit into this picture as a T-dual pair. Okay, so that means these two sides, they may have different topology. Okay, yeah, so this is the model of topological T-duality with H-flux formulated by these three guys. And more generally, there's a pair of principal torus bundles formulated by Bouwknecht-Evslin-Mathai, and Mathai. Okay, so if you consider the torus bundle case, this is very related to the Strominger-Yau-Zaslow conjecture. Considering the realization of Calabi-Yau manifolds and their mirrors as torus bundle over same space. Of course, at that time, they are singular fibers. But here, well, it's smooth. There's no singular fibers, non-degenerate. But it's very similar to this picture. So this is proposed in their famous paper, mirror symmetry is T-duality. Okay, so yeah, so I'm just explaining how to this picture related to your mirror symmetry picture. Okay. Yeah, okay. So yeah, so this is a pair. Then the next thing is several results have been proved, verified or coincide with the predictions of physicists. Okay, actually, to study such topological theory of such data leads to some new topological theories. Okay. So first, let's consider this simple thing: twisted cohomology. So suppose M is a smooth manifold, omega is a 3-form on M. Then you can simply twist the drum differential by this 3-form. So this D plus omega square equal to 0. So then you get a complex. But this complex is not a Z graded, it's a Z2 graded. So for this Z2 graded guy, you compute the cohomology of it. So this is something you get called twisted cohomology, twisted by this 3-form. Okay, this is Z2 graded. Now, if you specialize to M equal to Z, take this general manifold to be that circle bundle in that picture, and omega to be that flux. So then this has good physical meaning. Okay, so if you take an even form on the Z side, so it's actually so-called Raman field strength in type 2A field. So then you take odd form is in type 2B field. So then the thing is, okay, on this side, you have twisted cohomology. On this side, you also have twisted cohomology. So because these two guys, they are T-dual. So do they coincide? Okay. So here is okay. So like this is the T-dual. Then we consider something called the correspondence space. So we do the fiber product of the two circle bundles. Then here you get a torus bundle. So then the two sides, they interchange information through this correspondence space. Okay. Then by looking at this space, you can define some. You have something called a Hori map. So you take a form on the left-hand side. Then you take exponential of the so-called first chain class. Here it's actually decomposable as the wedge product of the two connection of the two sides. So this is actually the first chain class of the correspondence bundle there. What's the name of it? There's a name for this bundle or the correspondence. Poincare bundle. Yeah. Yeah. So then you integrate along the fiber of the Z side. Then you get a form on the Z head side. So this is actually a formulaic Fourier transformation. Okay. So then the Hori map sends forms from the Z side to the Z head side. And you can check that. So such a Fourier transformation give you isomorphism on twisted cohomology. Okay. So Yeah, so here there are two main ingredients. So geometrically, you consider the correspondence space. So and then you use a Horan map. So through the correspondence space to interchange information of the two sides. Okay, so this is the first thing you can verify to show the duality. Okay, the second thing you can do is twisted key theory. Okay. So we know that suppose M is a smooth manifold, we can consider key theory of the manifold or of the space. But suppose now you have a three form which has an integral period. Then we know a three form with integral period is the first Chern class of a germ. So then we can use this germ to twist the key theory. Okay, to twist the key theory. So then to twist this theory has a vast development in the previous years. So it starts from the work of Donovan Karobin, and then later Siegel and Fried-Hawkins-Telemann. So they related twisted key, equivalent twisted key theory to the Belinda formula. So something like that. Okay. So and for twisted key theory, we can also define twisted Chern class. Just like given a Euro vector bundle, we can have Chern class. But now for co-cycle in twisted key theory, which has so-called twisted bundles, we can also define twisted Chern class. Okay, so this has been studied by Atiyah Siegel using Atiyah-Hertzsprung spectral sequence, and Bouwknegt-Evslin-Mathai, Murray, Stevenson, this Australian school, they study twisted Chern class by doing the Chern-Wei theory. So you use a connection and a curvature to define the twisted Chern class. Okay, so this is a simple development of twisted key theory. Now, if you do the quantization of the twisted Chern class, if you quantize this theory, then you get the Mathai Melrose single fractional indexing. So this is a generalization of the traditional Atiyah single. We know in the traditional Atiyah single, we have a topological invariant called the A-hat genus, which is an integer on spin manifold. So then analytic interpretation is this integer is equal to the index of the Dirac complete. But now, suppose your manifold is not a spin anymore. So then the A-hat genus, that topological number is actually a fractional. Then what's the analytic interpretation of that? So Mathai, Melrose single, so they give a analytical interpretation of that. And actually physics, it's quite related to fractional quantum Hall effect. So for this picture. Okay. Yeah, and now we have twisted the key theory. We have twisted the cohomology. So then, well, how to remove this? Oh. Okay, so then we can define something called a twisted Chern character. We know that there's a cohomology functor from K theory to cohomology, the standard functor Chern character. Well, here you can, of course, you can take define by these five guys the twisted Chern character. Okay, and the twisted key theory has been used, so it's actually has a physical interpretation. So, for example, the K0 ZH is the home of the deep ring charge in type 2A3 theory. And K1, the odd twisted key theory, is the home of the deep ring charge in type 2B string theory. Okay, so this is the work of these guys, Australian school. Okay, and also in that paper of Bouwknegt-Evslin-Mathai, they also prove that there's also a so-called Horan formula for the key theory, twisted key theory. So related to the twisted key theory on both sides and give you isomorphism. Okay. Moreover, you have such a diagram. So this is a Hori map for the cohomology level. So this is a Hori map for the P-theory level. So you have isomorphism, and then on both sides, if you take twisted string character, you have a commutative diagram. Okay, so
you have a formula for the K-theory.
Yeah, you just throw back the theory to the correspondence space, and then take a K-theory forward. Basically means you take index, still you couple with the Bouwknegt bundle, and then do the push forward in K-theory. Yeah. So the idea is similarly. So just throw back everything to the correspondence space, couple with Bouwknegt bundle, and then push forward. Okay. So these are the two traditional theory: twisted cohomology and the twisted K-theory. So then you simply study the such a theory on both sides. You get the T-dual on both sides. Okay, now we go to some not that traditional story. So let's look at the theory from the loop space perspective. Okay, so in Atiyah-Witten Bismuth's work, so in those two papers I quoted at the very beginning, they study equivariant cohomology of free loop space and formally realized the Atiyah-Singer as a fixed point theory on free loop space. So this indicates, because now on both sides we have an index theory related theory, K-theory or cohomology. So this indicates that the T-duality with flux and the Hori formula for spacetime should be a shadow of T-duality and the Hori formula for free loop space. Because the index theory you can view it from the loop space, then naturally we want to say if the T-dual picture previously can be also seen from the free loop space on both sides. Okay, so yeah, under the free loops perspective, we mentioned some work. So one work is Bouwknegt-Evslin-Mathai. So they study twisted chiral drum complex on both sides and shows that they coincide. And I also have a work with Mathai to study some loop space on both sides and then verify some duality. Okay, well, later I will come to this point more detailed. Okay, but this is my so this is the main topic of today's talk, my talk. So we now we go one level up to consider double loop space on both sides. Why is it important? Because in string theory, so you consider this space-time is two-dimensional. So that means you map the genus one. Well, it's not complex. Well, now we first consider just the topological torus T2. We consider all the maps to Z. We call this double loop space. Now we take the double loop space on both sides. Okay. So then the thing is, can you see some duality on the double loop space level? Okay. So in this way, we have to study double loop space carefully and develop some theory on the double loop space. So this leads us to consider some theory of double loop space with the presence of a germ. Okay, now we have a germ or the three forms of flux. Now we consider the double loop space. What theory we have? So on such an infinite dimensional manifold. Okay, now so here what we find is this. We find that now suppose you have the germ, you have double loop space. We can then suppose I consider complex structure on the source. So we can do tall complex structure on the source. Then we can construct something called tall holonomic line bundle. So that means on the double loop space, well, it's a little bit different from double loop space. It's a little bit larger than that. We can define some holonomic line bundle coming from the germ and also affected by the complex structure of the source. We can define a line bundle. And on this line bundle, we can equip it with certain canonical connection. So that means even you forget the T-dual picture, the question is, suppose I'm manifold with a germ. If I look at the W space, what we can see? So the answer is we can see something called a tall holomy line bundle. So on the W space. Okay. So then let's consider the W space of both sides. We have both sides. We have those line bundles. Now we have such a picture. Question: do you have theory of connecting the both sides? So now it's the infinite dimensional theory. Okay. So yeah, we will explain the notations later. So this result, in some sense, is a T-duality with H-flux for 2D sigma model, because now you map the torus into your target, and also you consider the complex structure of the source. So this somehow answers the question of Hori, because Mathai said Hori asked him, how can you see the T-duality from this two-dimensional perspective? Okay. So here I will first very briefly introduce the germ in case some audience I'm not familiar with. Okay. So so now suppose you have a manifold with three form with integral period. So then the flux is the first Chern class of a germ. What's the meaning of it? So more precisely, so a germ on M is a collection of line bundle on double overlaps of open cover. Suppose you cover your manifold open cover, then on each U alpha beta intersection, you have a line bundle, complex line bundle. So it's such a system. Of course, you require those line bundles satisfy these co-cycle conditions. Okay, so this is one model of germ. So germ, there are many models. This is a certain model of germ. Okay. Actually, this is similar to a sheaf model. Okay, so and then this co-cycle thing give you a U1 value to check 2 co-cycle. So then that means you get H2 of M with value in S1. Okay, then the standard topology tells you you can get a degree 3 cohomology class over the manifold. So that is called the DD invariant of the germ. Okay, or the first Chern class of the germ. And up to equivalence, so the germ classified by H3, just like line bundles classified by H2, the germs classified by H3, or you can view it as a geometrization of H3 and Z. Okay. So then a trivial germ is simple. It's just you can decompose it to be those line bundles. So I will skip it. Kind of reason. Okay, yeah. So here is the intuition. So each intersection you have a line bundle. Okay, so here are some example of germ. So for example, here we have so-called spin C germ. So suppose M is orientable manifold. So but then the thing is it a spin C? Because if an orientable manifold, if you had a spin C structure, you can do a single. But usually, if it's not spin C, what's the obstruction? So the obstruction is a germ. It's spin C germ. Okay, so roughly speaking, that is on the intersection, you have a SON valued function. But for SON, if you do centric extension, you get spin C. But such centric extension, if you want to, you cannot glue them together. If you can glue them together, then manifold becomes spin C. So, but if you cannot glue them together, you get a germ. So this is obstruction. And the DD class of this spin C germ is the big W3, Steve Whitney class. Okay, another example is the so-called it's a PU bundle, PU germ. So you consider a classifies, a PU projective unitary bundle, principal bundle. Then the question is, can you lift it to be a quotient of principal U bundle? Then the answer is yes, you still have obstruction. So that is a term. So I will quickly. Okay. Now I will introduce a notion called B field, which is closely related to jerk. Okay, so a connection on the jerk with curving B field is such a kind of data. We know for jerk we have such a bouquet of line bundles, and now we equip them with connections, and we consider the curvature of these connections. Then this curvature is twofold. So a B field is just the forms on each U alpha or U beta, such that their difference give you the curvature of this line bundle on the intersection. So then you have a bunch of two forms. So you have each a two form on U alpha or U beta. So in physics, this is called a B field. Okay. Okay, now we just introduced the notion of jerk. Now we want to move to loop space or double loop space. Okay, now we have jerk, we have B field, this kind of notion. So what it tells us on loop space or double loop space. Okay, so given a jerk on M, so this gives rise to a line bundle over the free loop space. So this process is called a transgression. You transgress a jerk from the original manifold, you get a line bundle over the loop space. Okay, this is the standard thing. It's called holonomic line bundle. And to study loop space, we have to cover the manifold by something called Brzezinski cover. So because on loop space, if you want to cover it by open set, what is the right open set? You should use it to cover loop space. Okay, so then you take a Brzezinski cover, which satisfies these conditions. Then you consider the loops in this Brzezinski cover, which give you open cover of the loop space. So basically, it's like you consider loop in your manifold, you consider thickened loop around this loop, and then you consider all the loops in this thickened tubular neighborhood, and you use this way to cover all the loops. Okay, so this is the Brzezinski cover, and a connection on the jerk also give you a connection on this line bundle. So roughly speaking, so on your original manifold, you have a jerk with connection. Then by transgression, you get a line bundle with connection over the loop space. Okay, so that means if you go from manifold to infinite dimensional manifold, loop space, so your categorical number decreased by 1. So you go from jerk, which is a higher line bundle, then you go to honest line bundle over loop space. Now we quickly move to double loop space. So to study T-duality from the perspective of two-dimensional sigma model joined with Mathai, we give relevant construction and discover some properties over double loop space. So first, we of course want to cover the double loop space by double loop Brzezinski cover. Okay, so this is very easy. So just like if you take a double loop in your manifold, you consider the tubular neighborhood of it, and then use the double loops there inside this tubular neighborhood to cover the whole double loop space. This is the easy part. And also, we want to introduce some operation. See, we have a so-called evaluation map. You take a double loop, then you times T2, you have a map to your original manifold. So this is easy. You take a double loop, evaluate at time s and t. Should not call it at time, but yeah, then you get a point in the manifold. You have an evaluation map. Then you have a double transformation map. So that is, if you take a form on M, you pull back to the left-hand side. Then you integrate along the torus. then you get a form of degree less than 2 on the double loop space. So this is the standard operation over double loop space, the double transgression map. Okay. So then, but because you have double loop, you can do more. For example, you can integrate on one circle, but do average on the other circle. So this is called average after transgression. So on single loop space, you only have you have transgression and average. So on double loop space, you can do transgression, then average, or do double transgression. This kind of combination. Okay. Yeah. So I quickly. Okay. Then we can also do the double loop averaging. You take a form, you can double loop averaging. Drop it. And also, there are canonical maps from double loop space to single loop space. Yeah, so this is just okay. Now let's review. Suppose M carries a jerk with connection. So it's here H is a 3 form, it's flux. B alpha is a B field, and F alpha beta as a connection of the line bundle on the double cover on the U alpha beta. So then they satisfy this relation. So this H3 form, if you restrict to only U alpha, it's D of B alpha. And the B alpha minus B beta give you the curvature of the bundle on the intersection. And then on the triple intersection, you have such an isomorphism. So then such a tuple is called a Deligne co-cycle representation of the jerk. Okay, now suppose I'm given such a data. So M with the Deligne co-cycle. Now we want to construct something called an average holonomic line bundle. Okay, on the double loop space. So here is the construction. Okay, because now you have a double loop. So now you take the holonomic around the first direction, and then take a logarithm. Then you average on the other direction. You get a function. And then on the other hand, you do holonomic of the other direction first, and the average of the first direction. Then you multiply a tau there. So this tau represents the complex structure on the source. Then you get a function. This is a function on the intersection LLU alpha and LLU beta. Okay. So now this function, you can check that. You can check that it is invariant under the lead derivative of K1 plus tau K2. Okay, so K1 is a Killing vector field of the first circle. K2 is the second circle. K1 plus tau K2 is a complex vector field. Okay, so this complex vector field, if you flow it, you get nothing. Does not come from action of the circle. Okay, but this vector field has a very good thing. The zero of this vector field is just an n. So this is a vector field over double loop space, but the zeros of this vector field is just your original manifold. So and then for this G alpha beta, you can check that it's K1 plus tau K2 invariant. Okay, this is the first thing you can see. Now you consider the co-cycle comes from this G alpha beta stuff. Then you find that.
So sorry. So K1 and K2 are the killing field, right?
Yeah, of the two directions. Yeah.
And tau is a choice of complex number.
Yes, the tau is a number over upper half plane.
So how can that vector field be vanishing? I mean, there are two.
Oh, that means K1. So where K1 plus tau K2 both equal to 0.
Right.
Yeah.
So you're saying that the intersection of the vanishing locus of the two fields.
No, I think it's K1 plus tau K2 with an equivalent metric on the complex vector field. We require that metric equal to the non equal to 0. So that means,
Oh, okay.
yeah.
Okay.
Okay. Okay, then you consider the cocycle formed by those functions we define G alpha beta, then you find it's not equal to 1. Instead, it's equal to this number. If tau is integer, this is equal to 1. So that means, of course, then you get a good line bundle over W space. Unfortunately, you have a tau. Or in other words, if you consider the fundamental domain of the SL2Z action, only on the 2 cusps, so it's good. But on the other places, you don't get a line bundle. So how to solve this problem? We consider space a little bit larger than the W space. It's actually a circle line bundle or circle bundle over it. So this circle bundle comes from the polynomial of the single loop space, but because of time reason, I think I will skip this part. Anyway, so anyway, we get a line bundle over the so-called this W space, a circle bundle over the W space. We get a good line bundle. And moreover, on this line bundle, we consider such an operator. So this is the operator coming from the connection of the line bundle minus U iota K1 plus tau K2 plus U inverse to the double average of the flux. You consider such a so-called super connection. So this is the operator acting on differential forms over the extended W space valued in that line bundle. Why we should want to consider this operator? So if you calculate this operator, so you find that it satisfies this kind of relation. Okay, if you take a Lie bracket, then you get the Lie derivative, and then here you get 0. So such a kind of relation is actually such a super algebra form of super algebra. So this means what? This means a super circle acting on the complex. Okay, because such a relation comes from the Lie algebra of the super circle. Anyway, so this algebra considered in Witten's famous paper, supersymmetry and Moore theory. I mean, so such picture still fit into that supersymmetric picture. Okay, and then we consider such a complex. Now this guy square equal to Lie derivative. Suppose you consider K1 plus tau K2 forms of this guy, then you get a complex because this guy squared equal to 0 of this guy. Okay, question is, if you compute the cohomology of the complex, what do you get? The answer is you get the twisted cohomology of your original manifold. So yeah, so this is a localization proof by Mathai and myself. So this gives you what? This gives you a double loop space lifting of twisted cohomology. So, yeah, so this is basically twisted cohomology. So this is the story on the double loop space. If you restrict from double loop space to a fixed point, then you get a quasi-isomorphism. Okay, so it's a double loop space lifting of the twisted cohomology. So as I explained at the very beginning, twisted cohomology seems like purely algebra, no geometry. You simply twist the operator D by 3 form, right? It's just an algebra game. But what is the geometric content of it? Only on W space you can see it. You can see it. Because on W space or maybe loop space, the germ has geometrical meaning. The 3 form has geometric meaning, line bound or this kind of thing. Okay, so this is a Borel type localization. So that means if your manifold has a torus action or circle action, then equivalent cohomology of the manifold can localize to fixed point. So this is an infinite dimensional localization. Okay. Now we apply our theory to the T-dual pair. So then we can see that the theory of this side and the theory of this side coincide. Okay. But now we are lack of a Horin map on the double loop space level. Okay. this we only know that after localization, these two guys coincide, right? Yeah, so we use that. Okay, and then I will very briefly talk about some notion. Okay, so remember that when we construct that line bundle, that complex, it depends on a parameter tau. So then, for each tau on the upper half plane, we have a theory. We have a theory, right? So then we have a sheaf of those complex over the upper half plane. Okay, and you may ask me what's the global section of that sheaf? Yeah, so I want to say EDP genus or Witten genus is actually a global section of the sheaf. So, but with this twisting, so then a global set, twisted EDP genus serve as a global section of this sheaf on the upper half plane. Okay, and moreover, I consider the flux or the level of it, because for this flux, I can also consider H. I can also do MH. Consider, I mean, I assemble all the levels together. So we call this graded T-duality. Okay, and then for time reason, I will little bit skip. So we get eventually we get such a picture. We get a picture, say, so on the both sides, if you consider the using that sheaf coming from that complex and assemble all the level together, then you do all the levels Hori map, then algebraically you can assemble them to be such a theorem. So means you do graded Hori to the right hand side and do graded Hori back. Whatever you get the Euler operator. Okay, and so on. So then this gives you a more complete picture of the T-duality. So we call it a graded T-duality. Means you consider all levels of multiples of the flux. Okay, then we discover the Euler operator. Okay, yeah, I think that's all of my talk. So here are some reference, the Witten's famous paper, Yau Zaslow, Hori Vafa, and this my paper is Mathai, and this paper is Andy and